Hi everyone, this lesson is going to be about the technique we call data straightening. And as an example, let's take a look at this information here. This was represents the planets of the solar system, at least the ones that were known about 400 years ago when Johannes Kepler was studying these things. And so the period here represents the time taken for the planets to orbit the Sun, and as we can see, Earth has a value of 1. So the unit of measurement for these is normal Earth years. We can see Mercury and Venus both take less time to go around the Sun than the Earth does, and Mars, Jupiter and Saturn take much longer. The orbital radius, the distance from the Sun to the planet, again the Earth is a value of 1, and this is a measurement in astronomy known as the astronomical unit, the distance from the Earth to the Sun. So it's a convenient unit. Clearly 400 odd years ago Kepler didn't know that distance in miles or kilometres, but he did obviously know that it was a certain amount, and that the other planets were multiples of that. So Jupiter is a bit over 5 times further away from the Sun than the Earth is, and so on. Mercury and Venus are both closer. Now, how are we going to have a go at doing this? Well, first thing is to pop into your graphic calculator. Now, I'm in the statistics app there, and I've got the data here. To save time, I typed it in earlier. The radius data is typed into list 1. Now, because I'll probably forget, I'll put a letter R at the top of that list there. I can just type the letter R there under the subheading. And I've got the period data here, so I'll put letter P somewhere. There it is, letter P. Now, I want to do a graph of this, so I'll try F1. I've got 3 different graphs available to look at, so I'll look at the settings. The first stat graph is a scatter plot using X values in list 1, Y in list 2, which is right. So I will just go back to here and then I'll hit graph 1. There's my picture. Now, it doesn't look to me like a straight line. It looks like it's sort of a bit flat there, but then it suddenly looks like it's curving upwards here. So let's do a quick little sketch of that in our notes. It doesn't have to be an accurately drawn plot, but if I did a graph of period versus the orbital radius, the data points, they were rising slowly and then all of a sudden they jumped up. I might have exaggerated a bit there, but it certainly doesn't look like a straight line. So this might be an exponential function. Now, the way that we will be able to tell is, again, let's use the calculator. We'll exit from there. I'm going to calculate the logarithm of R in this list. So I'll go up to the top of list 3. It's very important that the cursor is at the top there so that whatever formula I type now applies all the way down list 3. And I will press log brackets. Now the word list is down here, so shift list 1, close brackets. Every number here in list 1, it'll take the log of this number and put the answer here. There they are. Let's see, can I type, I can probably type log there if I use alpha. That's just so I remember. It's the, where's L gone? L. Now, I'm just going to abbreviate. I'm going to go L brackets R, and this is really just for me to see what's going on. So it's just a label, log of radius. Let's go across to list 4. Now we're at the heading, so we'll do the calculation log of list 2. Let's check that's right. List 2 is period, yes. And I'll go up to that heading there and I'll just type a little bit there so I don't forget. L brackets, oops, did that one. It's period. So alpha P, where did you go P? Those letters are tiny, very hard to see. Again, the numbers what's important, the letters are just for fun, just to help us. So what I'm going to do now is a plot with list 3 as the x's and list 4 as the y's. Let's go into the settings. Now instead of using statgraph 1, which is already something I like, I'll go to statgraph 2 by pressing F2. And it's also a scatter plot, and it's list 3 then list 4. That's what I need. So let's go back there and I'll just press graph 2. That's looking like a straight line to me. I'm very pleased about that. Notice that there are 2 points here in the third quadrant with both negatives. Then there's a point right there. I wonder what that point at the origin would be. Then there are 3 more points over there. It looks like that's the point at the origin. Of course, because log of 1 is 0. So let's do a little sketch of this. Now this sketch was the log of R, and it was log of P. We had 2 data points there, 1 right on the origin, and then 3 data points over there. But importantly, it was a beautiful straight line. And we know that a straight line is given by a very simple equation, y equals mx plus c. That's why we're doing this, because a straight data straightening is all about getting a simple equation. Now the calculator can tell me the equation of this line if I press calculate, and then don't worry about all these fancy ones, it's under the X button here. Now the calculator doesn't use M and C, it uses A and B. So we'll just press this one. There's the numbers that I need. I'm just going to put that off to one side where I can see it, and I'll write this down. So according to the calculator, oops, I'll try that again. The y variable is the log of P. So I'll write log P. The gradient from my calculator was 1.5. Well, very close, 1.4999. So I'm going to go with 1.5. X variable is log R plus, and from the calculator, C equaled negative 0.001. That's close enough to 0 for me that I'm not going to worry about it. So there is my equation. Now, I could leave it like this, but I think we'll be better off if we neaten this up. So I'll go log P divided by log R equals 1.5. That's good. Then I could do change of base rule. That is log base R of P equals 1.5. And writing this as a power, I would have R to the power of 1.5 equals P. Yes, I think Kepler put P first, but it really doesn't matter, it's the same thing. Now, Kepler then, now we could stop there. This is a power law. We have the variable P, the variable R, and a power 1.5. Kepler decided that he would square both sides of this equation. So he would say P squared equaled, now power of a power we multiply, he would say P squared equal R cubed. And that formula there is the solution. It's known as Kepler's third law of planetary motion. And we've just managed to figure that out by looking at the raw data. We did a plot. I always like to do a plot of the raw data first, just to give myself an idea. It definitely looked curved, and that's what made me think it could be exponential. So a plot of logarithm of both is going to figure that out for me. Now, one last little thing about the calculator. Notice on this screen here we've got a copy and draw. If I press draw, it draws the equation of the line, and we can see what a good fit that is. If we're back at this screen, R squared value is the coefficient of determination. Now the best it could be is 1, and this is so close to 1 that it might as well be a perfect fit. The mean squared errors are very, very small as well, so that's another good indicator. If I pop back to graph 1 for a moment, you'll notice it has a calculation feature there as well. Now if I don't want a polynomial, I want a model that looks like p squared, or this one here really, power model. Do you notice we have a formula here for power model? There's my power model. A equals, so the power model, A equals 1. X is my x variable, which was r in this case, and to the power of 1.5. I can draw that one, and there's the power formula, the curved formula, which also fits beautifully there as well. Now, of course, we could have just done that straight away, but the purpose of this exercise is to do this the way Kepler would have done it, by using logarithms and plotting a straight line. It's much easier to solve a straight line graph if you're working without a calculator, as Kepler did, than it is to solve a curved graph. Okay, that's enough for now. Thanks for watching.